this is module 38 of the course on econometric modeling. We are at the last leg of the course. So, this is the last part, modeling long run relationships, and in that the first two modules are on stationarity and unit root testing. So, the first module, that is of these two, that is module 38, is on primarily the concept of stationarity and how we can deal with or remove stationarity. In the module 39, I will be discussing how to test for stationarity. So, a stationary time series process is one whose probability distributions are stable over time in the following sense, that if we take any collection of random variables in the sequence and then shift that sequence ahead each time periods, the joint probability distribution must remain unchanged. Formally, a stochastic process x t equals 1 to t is stationary if for every collection of time indices 1 less than equals to t1 less than t2 and so on, the joint distribution of x t1, x t2, x tm is the same as the joint distribution of x t1 plus h, x t2 plus h, x tm plus h for all integers h greater than equals to 1. So, this formal definition is actually complicated, but what it simply implies that first of all x t has the same distribution as t equals 2, 3 and so on. So, for all time periods the stochastic process x t will have the same distribution. And the second thing what it implies is that the joint distribution of x 1, x 2 must be the same as the joint distribution of x t and x t plus 1 for any t greater than equal to 1. This definition of stationarity refers to strict stationarity. Often we deal with something which is actually a weaker form of stationarity, and that is denoted by covariance stationarity. This stationarity was introduced also in the context of while we were discussing the univariate time series modeling, that is ARMA and ARMA processes. So, covariance stationarity is defined as a stochastic process x t with finite second moment if expected value of x t is a constant, variance of x t is a finite constant, and for any t h greater than equals to 1, covariance x t plus h depends only on h and not on t. So, this implies that if we are considering two time periods x t and x t plus h, that is we are considering the stochastic process in the two time periods, then the covariance between the two time periods would actually depend on the distance between the two time periods, that is h, and not on the time periods themselves. So, this implies that if I am considering time period 1 and time period 5, so there is a distance of 4, the covariance between them will be equal to the covariance between x x and x 11, where again we have x 10, where again we have a difference of 4. If a stationary process has a finite second moment, then it must be covariance stationary, but the converse is certainly not true. Covariance stationary processes are also called weakly stationary or second order stationary processes. This implies that the first two moments of the series are independent of time and the covariance between any two values of the series, although independent of time, is a function of the distance between the two time periods considered. A series which is not stationary is called a non-stationary series. Now, we consider a simple AR1 model. This is how we used to write an AR1 model, where we are considering one lag length of the AR term, that is this is an autoregressive process, the endogenous variable. We assume that ut, the error term, is identically and independently distributed with 0 mean and constant variance at sigma square. So, in this model the assumption that the mod value of rho is less than 1 is crucial for the series to be stable. Alternatively, we will prove that the conditions for stationarity hold if the mod value of rho is less than 1. So, we have mentioned so far the conditions that are required for stationarity, that a constant mean, a constant variance, that is they are not dependent on time, and covariance, which is basically a function of the distance between the two time periods, right, and again not a function of time. So, we can prove that for values of rho, mod values of rho less than 1, a series of this sort will be actually covariant stationary. So, let us rewrite 1 using lag operator or L as 1 minus rho L y t equals alpha plus u t. This lag operators are also introduced in the context of ARMA and ARMA processes. Now, we take, first of all I am taking y t minus 2 to the left hand side and then writing it as 1 minus rho L y t equals alpha plus u t. So, this implies that the moment I multiply a variable say y t with L, then I will be having y t minus the power of L. So, power of L is 1. So, y t minus 1. If I have L square y t, then this is actually y t minus 2 and so on. So, y t will be a alpha plus u t multiplied by 1 minus rho L raised to the power minus 1, because I am taking this to the other side. Now, 1 minus rho L raised to the power minus 1 can be expanded as 1 plus rho L plus rho square L square plus and so on up to infinity. And therefore, if alpha is multiplied by this expression, then of course we are having, since alpha is invariant of time, the lag operator does not have any role to or the operations to perform here. So, this is simply 1 alpha divided by 1 minus rho, and when I multiply this expression with u t, then I will be having u t plus rho u t raised to the power u t minus 1 plus rho square u t minus 2 and so on. So, basically we are summing over j equals 0 to infinity rho raised to the power j multiplied by u t minus j. Therefore, expected value of y t, I am now considering the expected value of y t, that becomes alpha divided by 1 minus rho, and this is a constant. You can see that this is independent of time, because expected value of u t is equals to 0. U t is an IIT process with 0 mean, and therefore, expected value of rho raised to the power j u t minus j will also be equals to 0. Now, we consider the variance of the series y t. Variance is calculated as expected value of y t minus expected value of y t whole square. So, we know that y t is first of all we know that y t is this expression. So, I am writing it here alpha divided by 1 minus rho plus summation j equals 0 to infinity rho raised to the power j u t minus j, and expected value of y t we just obtained as alpha upon 1 minus rho. So, alpha upon 1 minus rho, the entire thing whole square. Now, this expression is actually equal to sigma square plus rho square sigma square. So, if I expand this expression, then I will be first having u t, then rho u t minus 1, then rho square u t minus 2 and so on. And then if I take expected value, then first of all expected value of u t square is sigma square, then rho square u t minus 1 whole square. So, I have rho square sigma square, then rho raised to the power 4 sigma square. You notice that there is a raised to the power 2 sign. So, if I expand this, I will be having u t plus rho u t minus 1 plus rho u t minus 2 rho square u t minus 2 and so on, this entire thing raised to the power whole square. And since UTs are IIDs, that is identically and independently distributed, any cross multiplication between these components will be 0. So, we just need to consider the square terms of these individual components, and as a result of which I will be and taking expected value of those square terms, I will be arriving at sigma square plus rho square sigma square plus rho raised to the power 4 sigma square and so on. And then again it will be an infinite series of 1 plus rho square plus rho raised to the power 4 and so on. That is how we have sigma square upon 1 minus rho square. This is also a constant. So, therefore, variance of yt will be greater than 0 for mod value of rho less than 1. See, variances always have to be greater than 0 or positive numbers. That is ensured by the fact that mod value of rho is less than 1, and that is why this is an important condition other than ensuring stability. Now, considering the covariance between yt and yt minus 1, how do we write covariance between yt and yt minus 1? This is actually expected value of yt minus expected value of yt minus 1, sorry, then yt minus 1 minus expected value of yt minus 1, right. So, we have yt into expected value of yt is alpha divided by 1 minus rho, then yt minus 1 minus expected value of yt minus 1, which will also be the constant alpha upon 1 minus rho. Now, multiplying, I have this expression. You can see that expected value of yt is rho alpha divided by 1 minus rho. So, we have alpha square 1 minus rho square minus alpha square 1 minus rho square. So, we have actually minus 2 alpha square 1 minus rho square and 1 alpha square divided by 1 minus rho square. So, therefore, we have finally expected value of yt minus 1 as it is coming here minus alpha square 1 minus rho whole square. Let us denote expected value of yt minus tau by gamma tau for tau equals 0, 1, 2 up to t. Now, multiplying both sides of 1 by yt minus 1. So, equation 1 was this AR1 model. I am now multiplying both sides of this equation by yt minus 1. So, we have on the left hand side yt into yt minus 1. On the right hand side, I have alpha into yt minus 1, rho into yt minus 1 square and then ut into yt minus 1, taking expectations all along. So, first of all, I have gamma 1 here, because you can see that expected value of yt minus tau is gamma tau. So, tau actually is the difference between the two time period. Here the difference between the two time period is 1. So, I am having gamma 1. Now, gamma 1 would be equal to this expression. Now, we can see that expected value of yt minus 1 is alpha upon 1 minus rho. So, this become alpha square into 1 minus rho, and then for the rest this is actually rho into gamma 0. You can see that this can be written as expected value of yt minus 1 into yt minus 1. So, there is actually the distance between these two is 0. So, we denote it by gamma 0, rho gamma 0, and this is equals to 0, as we have earlier assumed that UTs are identically and independently distributed. So, substituting this expression in the expression for covariance between yt and yt minus 1. So, this was my covariance expression for covariance. So, first of all, I have expected value of yt minus 1 minus sigma square 1 minus rho square. So, covariance between yt into yt minus 1 has the last component, and expected value of yt minus 1 is actually replaced with alpha square into 1 minus rho and rho gamma naught, right. Now, similarly, we can find out that yt covariance between yt and yt minus 2 will be gamma 2 minus alpha square 1 minus rho whole square. The expression or the calculations are mentioned here. So, from 2 it follows directly from 2, this is expression 2, it follows that if gamma 1 is alpha square divided by 1 minus rho, which remains as it is because it is not dependent on either the distance or time period, plus rho gamma 0, then I will be having rho gamma 1. So, here gamma 0 is basically 1 less than the one which I have on the left hand side. So, here I have gamma 1 because this is 1 less than the one that I have on the left hand side. So, substituting the value of gamma 1 in 3, this is my expression 3, and we substitute the value of gamma 1 3, we have gamma 2 equal alpha square divided by 1 minus rho plus alpha square rho divided by 1 minus rho plus rho square gamma 0. Therefore, covariance between yt minus 2, which was gamma 2 minus this, is basically this expression. So, following this iterative process, it can be shown that covariance between y t and y t minus tau is actually, this is y and this is t minus tau, is rho raised to the power tau gamma 0, and then we have alpha square divided by 1 minus rho taken out common, and we have 1 plus rho square and so on up to rho raised to the power t minus 1, and then this again the component remains as it is. Suppose we call it lambda tau. So, lambda tau basically refers to the covariance between y t and y t minus tau. Now, note that lambda 0 is basically variance of y t, because covariance between y t and y t is actually variance of y t. So, when we do have tau equals to 0, then we have y t and y t, which is equal to variance of y t. Variance of y t is basically expected value of y t square minus expected value of y t whole square, and this is actually gamma 0, because y t is gamma 0 minus alpha square 1 minus rho whole square. This actually we have already derived. Therefore, gamma 0 is lambda 0 plus this thing. So, lambda 0 plus this thing taken to the left hand side. Lambda 0 is sigma square upon 1 minus rho square and plus alpha square 1 minus rho whole square as it is. So, this is actually a constant. That is how we have derived that the expected or the variance of y t is actually constant. From expression 4, it is clear that the covariance of the process in 1 will converge to a constant value only if mod value of rho is less than 1, right. So, this is my expression for this, shows that we have convergence only if the mod value of rho is less than 1. If the mod value of rho is greater than 1, then of course, as the power increases, there will be more and more divergence. Therefore, the stationarity condition is that the absolute value of the coefficient of the one period lagged value of the dependent variable of an AR1 series must be less than unity. Two alternative statements of the stationarity conditions are: the coefficient of y t minus 1 must lie within the unit circle, the absolute value of all the roots of the polynomial lag operator 1 minus rho L equals to 0 must lie outside the unit circle. Here 1 minus rho L equals to 0 has a single root equal to 1 upon rho. Therefore, mod value of 1 upon rho greater than 1 or mod value of rho less than 1 is the stationarity condition. If mod value of rho is equal to 1, then there is a unit root problem, as the root of the polynomial lag operator becomes unity. Further, if the roots of the characteristic equation are greater than unity, that is when mod value of rho is greater than 1, the series can be called an explosive series, or the series is actually an explosive series. Okay. So, now we talk about the properties of having a non-stationary process. So, non-stationary processes are generally highly persistent. So, now I discuss why do we call it a highly persistent series. So, many economic time series are better characterized by an AR1 model with rho equals 1. So, let us write the AR1 process as yt equals yt minus 1 plus ut. So, for the time being, I have dropped any constant term. It is simply yt equals yt minus 1 plus ut. So, you can understand the coefficient of the lagged observation or value lagged variable is actually equal to 1. We assume that the initial value y naught is independent of ut for all t greater than or equal to 1. The process in 5 is called a random walk, a special case of unit root process. The name comes from the fact that y at time t is obtained by starting at the previous value yt minus 1 and adding a 0 mean random variable that is independent of yt minus 1. So, basically the entire process, the changes whatever we are observing in yt, that is generated by the random component. So, it is absolutely random. If we remove that randomness, my current observation would be exactly equal to my previous observation. the entire movements in yt is caused just by the random term, that is the disturbance term, and that is why it is called a random walk process. By repeated substitution in equation 5, what we will get is yt expressed as ut plus ut minus 1 plus and so on, thus plus u1 and the initial value which is y naught. Taking the expected value of both sides, I will have this equals to expected value of y naught. This is because expected value of all these error terms for each and every time period is equal to 0 by assumption. So, for all t greater than equals to 1, expected value of yt is actually equal to expected value of the original observation or the initial observation y naught. Therefore, the expected value of a random walk does not depend on t. A popular assumption is that y naught equals to 0, in which case expected value of yt equals to 0 for all t. By contrast, the variance of a random walk does change with t or it depends on t. For simplicity, let us assume that variance of y naught is equals to 0. Then we have variance of yt is actually sum of variance of ut minus 1 and plus variance of u1. Again, we do not have any cross multiplication or cross terms because all these u's are identically and independently distributed. So, we have sigma square u, sigma square u, sigma square u summed for t times. So, that is why the variance of yt is sigma square u t. This shows that the variance of a random walk increases as a linear function of time and the process cannot be stationary. Even more importantly, a random walk displays highly persistent behavior in the sense that the value of y today is important for determining the value of y in the very distant future. To see this, write equation 6 for h period ahead. This was my equation 6. So, I write it for h period ahead as yt plus h equals to ut plus h and so on. Finally, ut plus 1 and then we have plus yt. At time t, the expected value of yt plus h is actually yt because all the expected values of ut's are equals to 0. So, this happens for all h greater than equal to 1. This means that no matter how far in the future we look, our best prediction of yt plus h is today's value yt because we cannot predict anything about the random component, right. In contrast to this, a stable AR1 process will have expected value of t plus h conditional upon yt is equal to rho raised to the power h yt for all h greater than 1. And since stability requires mod value of rho greater than less than 1, then of course you can see that as h increases, then rho raised to the power h becomes actually smaller, right. Therefore, expected value of yt plus h conditional upon yt approaches 0 as h tends to infinity. That is the value of yt becomes less and less important and expected value of yt plus h conditional upon yt gets closer and closer to the unconditional expected value, that is expected value of yt equals to 0. Also, if variance of y not equals to 0, it can be shown that the correlation between yt and yt plus h is actually root over t upon t plus h. Thus, the correlation depends on the starting point, that is t, and it becomes closer to 1 for large t when the sequence yt follows a random walk. Further, although for fixed t the correlation tends to 0 as h tends to infinity, it does not do so very quickly. In fact, the larger t is, the more slowly the correlation tends to 0 as h gets larger. So, that is why we call this series highly persistent series. Now, let us consider stock prices as an example. The dynamics of the price process is given by St equals St minus 1 plus ut. So, St refers to stock price. So, today's stock price is yesterday's stock price plus some random component, or the change in today's stock price is actually equal to today's random component. So, it is not at all explained by anything other than that. This implies that tomorrow's price, that is St plus 1, is thought of as today's price plus some random shock that is independent of the price. As a consequence, in this model the increment st minus 1 from t minus 1 to t are thought of as completely undeterministic. We cannot determine it. Since the UTs have a mean of 0, the increments are considered fair. An increase in a price is likely as a downside movement. At time t, the price is considered to contain all information available. So, at any point in time, next period's price is exposed to a random shock. Consequently, the best estimate for the following period's price is this period's price or today's price. Generally, it is not easy to look at a time series plot and determine whether it is a random walk or not. So, there is no shortcut or straightforward way of determining it just by looking at the series. It is extremely important not to confuse trending and highly persistent behaviors. A series can be trending but not highly persistent. It is also often the case that a highly persistent series also contains a clear trend. So, the trend, the way we have understood it so far or discussed previously, that it is a deterministic trend, and it is sometimes possible that a highly persistent series, that a random walk series also contains a clear cut trend. One model that leads to this behavior is the random walk with drift. So, this is a series with random walk with drift. You can see that this is very similar to the AR1 model that was considered in the beginning, except for the fact that here rho has taken the value 1. So, alpha naught is called the drift term. For such a series, the expected value of yt follows linear time trend by using repeated substitution. So, if I go for repeated substitutions of yt minus 1, that is yt minus 1 will be replaced with alpha naught plus yt minus 1 plus ut minus 1, and similarly for yt minus 1 and so on. So, I will be having actually t alpha naught terms. So, I have alpha naught multiplied by t, then ut minus 1 and so on plus u1, and finally the initial observation which is y naught. Therefore, if y naught is equals to 0, expected value of yt is alpha naught t. So, you can see that now the expected value of yt grows over time if alpha naught is greater than 0, and it shrinks over time if alpha naught is less than 0. But overall the fact is that the expected value is actually a function of time, and it is not constant the way we want covariance stationary series to be. The variance of the series is variance of yt equals expected value of j equals 0 to t minus 1 ut minus j whole square, and this is so because the other components like alpha naught t is constant, it cannot have any variance, and y naught is assumed to be 0. So, it also does not have any variance. So, the other terms, that is the uts, are actually summed up and their squares are taken. So, this turns out to be t sigma square. We will be having t sigma square terms. So, adding them we have t sigma square. Therefore, neither the mean nor the variance of the process is constant, rather they are functions of time which violates the first two conditions for stationarity. Similarly, it can be shown that the covariance between any two terms will be a function of time. Suppose y naught is equal to 0, then it follows that covariance between yt minus 1, which is basically expected value of yt minus 1 minus expected value of yt multiplied by expected value of yt minus 1, is actually, this expression comes as it is minus alpha naught square t into t minus 1. This is because expected value of yt is alpha naught t, and expected value of yt minus 1 is alpha naught t minus 1. So, that is why I have alpha naught square t into t minus 1. And we can find out that expected value of yt minus 1, which is basically multiplying this series by yt minus 1 and taking expected values, gives us this expression. So, therefore, covariance between yt minus 1 is sigma square t minus 1, then we have plus alpha naught square t minus 1 and then minus alpha naught square t into t minus 1. Rearranging terms, I will be having this expression. So, generalizing this expression, we get covariance between yt minus 1 is sigma square t minus tau. Here the distance was 1. So, I have t minus 1. If the distance is tau, then I have t minus tau minus alpha naught square into t minus tau whole square for any tau. And this shows that the covariance is a function of time as well as the distance between the two time periods considered. Therefore, the third condition under weak stationarity is also violated, as the covariance between any two values of the series is a function of time. In order to make the initial presentation simple, the problem of unit root is considered in an AR1 series. However, the argument is valid also for higher order autoregressive processes. For instance, consider an ARP process as follows, that yt equals alpha plus rho 1 yt minus 1 plus rho 2 yt minus 2 and so on plus rho p yt minus p plus ut. Again ut is IID 0 sigma square. Now, equation 7 can be rewritten in the lag operators like this. The stationarity condition is that all the roots of the polynomial lag operator, this is the polynomial lag operator, should lie outside the unit circle. So, for one AR1 process, the polynomial lag operator was 1 minus rho L equals to 0. For ARP process, this is the polynomial lag operator and its roots should lie outside the unit circle. This condition implies that the sum of all the coefficients must be less than unity, that is rho 1, rho 2 plus rho p all together must be less than unity. If the variable employed in a regression model are not stationary, then it can be proved that the standard assumptions for asymptotic analysis will not be valid. In other words, the usual t ratios will not follow a t distribution and the f statistic will not follow an f distribution and so on. Therefore, before proceeding to econometric estimation, time series analysis requires testing for the presence of unit roots or non-stationarity in all the data series considered in a model. However, before discussing the testing procedure, let us first focus upon how to convert a non-stationary series into a stationary series. A series with one unit can be transformed to a stationary process by differencing the series once. So, for instance, we consider a random walk series with drift. This is a random walk series with drift. If yt minus 1 is subtracted from both sides of 8, then the new series becomes, you can see yt minus 1 goes to the other side. So, on the right hand side I am left with alpha plus ut, or delta yt minus 1 is equal to alpha plus ut. Now, expected value of delta yt is actually equals to alpha, given that expected value of ut is equals to 0. And we can also find out that variance of delta yt will be simply the variance of ut, which is equal to sigma square. Therefore, the series in 8 fulfills the first two conditions required for stationarity. Since there is no lagged value of the dependent variable on the right hand side, the covariance is 0. Similarly, if there are two units, then the series must be differenced twice to make it a stationary series. Thus, it can be generalized that a non-stationary series with d unit roots, d greater than 0, should be differenced d times to make it stationary. With d unit roots, a series is said to be integrated of order d and is denoted by id. D is the order of integration. Now, I conclude this module with this graph, which basically plots stationary series against a non-stationary series. So, first of all, this yt is a non-stationary series. So, the figure plots a random walk series yt equals yt minus 1 plus ut based on a starting value of y naught equals to 0. As can be seen, the variance of yt is increasing with time and there is no tendency for the series to revert to any mean value. The variance of the series actually is increasing with time. Now, this is delta yt. So, a random walk series, when differenced for once, it becomes a covariant stationary series. So, this is actually in contrast with the stationary first differenced series. Stationary variables can be seen to fluctuate around their mean, which is equal to 0 here in this case, because expected value of ut is equals to 0 and it has a finite variance. So, you do not observe the series to deviate much over a period of time from its mean value, the deviation remains constant. So, that is primarily about the stationary series, what kind of problem it poses, and how we can probably consider take care of stationarity. So far that has been discussed. These are the references that I have consulted. So, in the next module I will continue with the testing of stationarity, and after once we test for the presence of stationarity, then we have already discussed how we can correct for the presence of stationarity, and alternative is basically going for cointegration or cointegrated models, that will be taken up in the last module. Thank you.